Hi, this is Stu Schwartz from MasterMathMentor.com. This is video Precalc 06A, and the topic is solving oblique triangles. Back in geometry, we learned to prove congruence of triangles. That is, when two triangles are exactly the same. We use several rules to prove congruence. First, angle, side, angle. If two angles and the non-included side of triangle A is equal to the two angles and the non-included side of triangle B, then triangle A is congruent to triangle B. We then move to angle, side, angle. If two angles and the included side of triangle A is equal to the two angles and the included side of triangle B, then triangle A is congruent to triangle B. Next, we had side angle side. If two sides and the included angle of triangle A is equal to the two sides and the included angle of triangle B, then triangle A is congruent to triangle B. Finally, we had side, side, side. If all three sides of triangle A are equal to all three sides of triangle B, then triangle A is congruent to triangle B. In trig, we take things a step further. If we know, for instance, the values of two angles and a side of a triangle, then we can solve that triangle. That is, we can find the other angle and the other sides. So we're not just proving congruence, we are solving the triangle, which means getting all the information about it. We learned to solve right triangles in Unit 3, but in this section we will learn how to solve oblique triangles, triangles that do not have a right angle. As before, we will start with this generalization. All triangles will have 6 pieces of information, 3 angles and 3 sides. We will label the angles as capital A, B, and C, and the sides are opposite the angles and are labeled lowercase a, b, and c. We work with either acute triangle ABC shown in blue or obtuse triangle ABC shown in green. In either case, we drop a perpendicular from C down to line segment AB. In the case of the obtuse triangle, we have to extend line segment AB. Let us call that perpendicular H. So, in either picture, the sine of A is equal to opposite over hypotenuse, which is H over B. And the same thing is true for sine B, which is equal to opposite over hypotenuse, or H over A. And therefore, H is equal to B sine A, and H is equal to A sine B. And therefore, A sine B is equal to B sine A. And doing division, we end up with A over sine of A is equal to B over sine of B. The argument we just showed worked with angles A and B, but it can work with any two pairs of angles. So we now introduce the law of sines that says if triangle ABC is a triangle with sides A, B, and C, then little a over sine of A is equal to little b over sine of B, which is little c over sine of C. So the law of sines is really 3 laws in one. Little a over sine A is equal to little b over sine B. Little b over sine B is equal to little c over sine C. And little a over sine A is equal to little c over sine C. In each one, there are 4 variables. If you know 3 of them, you can find the 4th. The law of sines can also be expressed as Little a over little b equals sine a over sine b. Little b over sine c equals sine b over sine c. And little a over little c is equal to sine a over sine c. This says that the ratio of sides in a triangle equals the ratio of the sines of the angles. The law of sines works well with angle, angle, side. In example 1, we are told that angle A equals 23 degrees, angle B equals 48 degrees, and little a is equal to 14. We make a picture that describes this situation. It isn't really necessary, but it will help us to see the relations between the sides. To solve the triangle, we first determine angle C, which of course is 180 minus 23 minus 48, which is 109 degrees. We now set up the law of sines, and using it with the A and the B family, we solve for little b and get little b is equal to A sine B over sine A. We plug the information into our calculators and get 26.63. To find little c, we will use the A and the C family. It is always best to work with families of information, whether it's the A family, the B family, or the C family, which are given the information. Since we are given information about angle A and little a, we prefer to work with that as one of the families. So again, using the law of sines, we can solve for little c, which is equal to little a sine c over sine of a. Again, we punch the numbers in on our calculator and we get 33.88. Shown is the solution of the triangle. I like to box the information we just calculated to distinguish it from given information. To check, the smallest angle should be opposite the smallest side and the largest angle should be opposite the largest side. They are. Notice though that angle C is a little bit more than doubled angle B, but little c is not nearly doubled little b. That is because the law of sines says that the sides are not in the proportion of their opposite angles, but the sines of the proportions of the opposite angles. That is why the picture is helpful in verifying that the solution makes sense. The law of sines works equally well with angle, side, angle, because once you have two angles, you can easily find the third. In example 2, we have A equals 72.4 degrees, C is equal to 38.7 degrees, and little b is equal to 3.8 inches. Again, we draw the picture, attempting to draw it somewhat to scale. Compare the picture in example 1 to example 2. Angle A is in the same position, but B and C are switched. But it makes no difference where you put your angles. It is only important that when you draw it, they look somewhat similar to the given information. We first find angle B, which is 180 minus 72.4 minus 38.7, which is 68.9 degrees. We need to work with the B family because that is the only side we know. So we will work to find A, and we get little a is equal to B sine A over sine B, and little a is equal to 3.88. To find little c, we again prefer to work with the B family as that was a given side. So little c is equal to B sine C over sine B, and we get little c is equal to 2.55. Shown is the solution. Notice that the sides A, B, and C are measured in inches because B was measured in inches. Notice that the largest angle A is opposite the largest side A, while the smallest angle C is opposite the smallest side C. Since angles A and B are close in values, the same can be true with little a and little b. It is also always necessary to do this type of check because you are completely reliant on your calculator, and whatever the calculator will tell you, you will believe. So make sure that your answer makes some sense. If you were like me when you took geometry, you may have wondered why SSA, side-side angle, was not a rule for congruence. The problem with SSA is that while two sides of an angle may identify a triangle, it is possible that the triangle may not exist with that information. Or it is possible that two sides in an angle may identify two possible triangles. So let's examine the SSA situation more in depth and find that it breaks up into 6 possible cases. For all the 6 cases, we will assume that you are given little a, little b, and angle A. To establish the case, we first look at angle A. If angle A is obtuse, we have 2 possible cases, 1 and 2. In case 1, if little a is less than little b, it is impossible to draw the triangle. Looking at the picture, it should be obvious why. Angle A fixes the position of little b and little c. It is impossible then to draw a line of length A, which is less than b, to get down to side C. And if that is too complicated for you, realize that in any triangle, the largest side must be opposite the largest angle. A is the largest angle, so little a must be the largest side. Looking at the example below it, we see that angle A is equal to 114 degrees, little a is equal to 14, and little b is equal to 20. Based upon the situation that is given, this must be case 1, and there is no such triangle possible. In case 2, we still have an obtuse angle A, but now A is greater than B. Since angle A is fixed, there is only one way to draw the line from point C down to line segment AB. So one triangle is possible. So in the example, we have A equaling 114 degrees, but now A is 20 and B is 14. Since A is greater than B and we still have an obtuse angle, there is one triangle possible. Note we are not getting into right now how to solve the triangle. First of all, we need to ascertain that the triangle is possible. And it is, and there is only one way to draw it. Cases 1 and 2 were relatively simple. When A was obtuse, there was either no triangle possible or one triangle possible, based upon the relative size of little a and little b. The problem comes when capital A is acute. We will see that there are 4 cases. The simplest case is when capital A is greater than capital B. When we draw the acute angle, again, it fixes angle A in a certain position. And that means that once we have little b, there is only one way to draw side little a down to line segment AB. So there is one triangle possible. So in the third example, we have capital A is equal to 67 degrees, little a is equal to 18, and little b is equal to 11. Since we have an acute angle and little a is greater than little b, there is one way to draw this triangle. Case 3 worked with acute angle A and little a greater than or equal to little b. Now we still have acute angle A, but now little a is less than little b. We will see that this divides into 3 possible situations, which we will call cases 4, 5, and 6. In all cases, we will draw the altitude, the perpendicular line from C down to line segment AB, and we will call that H. In case 4, notice that little a is less than h. It should be clear that this triangle cannot be drawn. And in case 4, there is no triangle possible. In case 5, we again draw our perpendicular line from C down to line segment AB and call it H. And in this case, A is exactly equal to H. That means that this line is perpendicular and there is only one way of drawing this triangle. This turns out to be a right triangle with angle B equaling 90 degrees. Case 6 is the tricky one. We still have acute angle A, and we still draw our perpendicular H from C down to line segment AB. But now, little a is greater than h. And you can see by the picture that there are 2 possible ways of drawing this triangle. A, B, C, and A, B prime, C. So 2 triangles are possible. This is called the ambiguous case. Ambiguous means that it has more than one meaning. And what we're saying is that when we get this situation, it is entirely possible that there will be more than one triangle possible. That is the reason that SSA is not a reason for congruence. Some teachers require students to memorize the conditions and conclusions of these 6 cases. I don't. The main reason that H is not given. So the way to do this is to attempt to draw the triangle. In 95% of the cases, you will know whether 2 triangles are possible with the given information, 1 triangle, or it is impossible. Let us see some examples. In example 3, A equals 62 degrees, little a equals 5, and little b is equal to 15. In the picture, angle A is fixed, which means that the position of little b is fixed. Little a, opposite angle A, can be anywhere along that arc from point C. But it should be clear that no matter where it is drawn, it is not long enough to hit the line segment AB. This is case 4, where A is less than 90 degrees and A is less than B, and that means the triangle is impossible. The case number is not important. Different books will number these cases differently. What is important is the conclusion. In number 4, A equals 31 degrees, little a equals 22, and little b is equal to 9. In drawing the picture, again, angle A is fixed, which means that the position of little b equaling 9 is fixed. It should be clear then that it is possible to draw a line segment of length 22 from C down to line segment AB, wherever B is. So this is case 3, where A is less than 90 degrees and little a is greater than or equal to B. There is one triangle possible. In number 5, A is 99 degrees, little a is 9.2, and little b is equal to 5.5. Again, the angle is fixed, fixing the 5.5. We need a length of 9.2 to come down to hit line segment AB wherever B is. It should be clear that this is possible in only one way. This is where case 2, where A is greater than 90 degrees and little a is greater than B, and that means that there is one triangle possible. In number 6, we're told that A is 125 degrees with little a equals 16 and little b is equal to 30. Drawing the picture, angle A is fixed, meaning that the 30 is fixed. It should be clear that it is impossible to draw a line of length 16 down to line segment AB. No matter where we draw it along that arc, it will be impossible to reach line segment AB. So this is case 1, where the angle is greater than 90 degrees and little a is less than or equal to B. The triangle is impossible. In number 7, we have A equaling 30 degrees, little a equals 7, and little b is equal to 14. In drawing the picture, it is not clear whether a line segment from C of length 7 will be able to reach line segment AB. However, realize that if the angle is 30 degrees and little b is twice A, that means that this is a 30, 60, 90 triangle, and there's only one way to draw it. This situation occurs very, very rarely. Most of the time we are working with oblique triangles where the angles in the triangle are not equal to 90 degrees. In number 8, we have A equaling 25 degrees, little a is equal to 11, and little b is equal to 14. When we draw the picture, we find that the angle is fixed, which means that little b of 14 is fixed. We need a line of length 11 to come down and hit line segment AB. 11 is not that far below 14, and it should be clear that it is possible to do it, and in two ways, where the line segment starts at C, goes down to the right, or starts at C and goes down to the left. So this is case 6, where A is less than 90 degrees and little a is less than B, and there are two triangles possible. There are just a few times where, when making a picture, you still don't know whether the triangle can be drawn. Here are two cases that dramatically illustrate this situation. In both cases, we have A equals 38 degrees and little b equals 21. But in number 9, we have little a equals 12.9, while in number 10, we have little a is equal to 13. Just a slight difference. To determine whether these triangles are possible, we will draw these pictures exactly to scale. We see angle A as 38 degrees, fixing line segments AB and AC as 21. We need a line of length 12.9 to come down from point C to hit line segment AB. Notice wherever we draw the red line of length 12.9, it just misses the blue line AB. The closest it gets is the perpendicular, but it still just misses. So we conclude that this is case 4, where A is less than 90 degrees and little a is less than little b, and the triangle is impossible. We have the same picture drawn to perfect scale in number 10, but now the length of the line coming down from C is 13, just a hair longer, and that extra length makes a difference. Not only does the green line of length 13 hit the horizontal line, it hits it in two locations that we will call B and B prime. We went from a non-possible triangle in number 9 to two possible triangles in number 10. In most situations, whether this is case 4 or case 6, no triangles or two triangles, will be obvious by drawing the triangle with the given variables. But sometimes it's too close to call, even if the triangle is drawn perfectly to scale. Thankfully, there is a mathematical way to determine this information that is not dependent on the picture. It is based on the law of sines. The law of sine says that little a over sine A is equal to little b over sine B. We cross multiply and solve for sine B and get little b sine A over little a. So, assuming that we have an acute angle A less than 90 degrees and little a is less than little b, we look at the value of sine B. And if sine B, which is little b sine of A over little a, is greater than 1, this is impossible because the sine of a function cannot be greater than 1, and that means the triangle is impossible. However, if sine of B, which is little b sine A over little a, is less than 1, there are two triangles possible. So, for problem number 9 above, we will look at sine B, which is 21 sine of 38 degrees over 12.9. And when we calculate that with full decimal place accuracy, we get 1.00224. And that number is just barely greater than 1. And that's telling us that there are no triangles possible. The fact that it is so close to 1, but still over 1, tells us that it's very close, as we've seen. In number 10, we look at sine B to be 21 sine 38 degrees over 13. And now we get 0.99453, and that is less than 1. That tells us that we have two triangles possible. Again, because it is so close to 1, it is telling us that it is still a very, very close call. So just that little difference in the size of little a can make a difference between problem 9 and problem 10. But our calculator will tell us whether there's no triangles possible or two triangles possible. It is important to note that this phenomenon only occurs in a side-side angle situation. Angle-side angle and angle-angle side are always defined with one and only one triangle, and the law of sines solves these problems easily. Now that we have decided how to determine whether or not an SSA problem has a solution, we now need to actually solve the triangle. Again, let's assume that we are given little a, little b, and angle A, and we have verified that the SSA problem has only one solution. There are 4 steps. First, we need to find angle B by using the fact that sine of B is equal to B sine of A over little a. And therefore angle B is equal to the inverse sine of B sine A over A. Once we have angle B, with the knowledge of angle A, we can find angle C by using the fact that C is equal to 180 degrees minus A minus B. And then finally, we will use the law of sines with the A family, which we know, and the C family, using A over sine of A is equal to C over sine of C, and therefore little c is equal to little a sine C over sine of A. Finally, we need to quickly verify our answer by checking to see whether the largest side is opposite the largest angle and the smallest side is opposite the smallest angle. So let us look at two previous SSA problems where we've ascertained that there is one triangle as a solution. Number 10 is a repeat of problem 4, where angle A was 31 degrees, little a was 22, and little b is 9. So we start by going for B, which is the inverse sine of little b sine A over little a. And that is the inverse sine of 9 sine of 31 degrees over 22. And we get 12.16 degrees. Now, angle C is 180 minus 31 minus 12.16, or 136.84 degrees. And now we use the law of sines with the A and C family, and little c is A sine C over sine of A, or 22 sine of 136.84 degrees over the sine of 31 degrees. And we get 29.22. Again, we box the values that we found, and B is 12.16 degrees, angle C is 136.84 degrees, and little c is 29.22. Again, the largest angle, which is C, is opposite the largest side, and the smallest angle, B, is opposite the smallest side. 11 is a repeat of problem 5, where A is 99 degrees, little a is 9.2, and little b is 5.5. Again, angle B is inverse sine of B sine of A over A, or the inverse sine of 5.5 sine of 99 degrees over 9.2, and we get 36.19 degrees. C is therefore 180 minus 31 minus 36.19, which is 44.81 degrees. And little c is equal to A sine C over sine A, which is 9.2 sine of 36.19 degrees over the sine of 99 degrees, which is 6.56. When you do these problems, it is recommended that you show on exams your formulas. Most of the problems are done on the calculator. And if you make a mistake, your teacher will have no idea what you did wrong. So showing that you know what formula to use will cover you in case you type in something incorrectly. Our final answer of B being 36.19 degrees and angle C being 44.81 degrees and little c equals 6.56 are in the correct proportions. The largest angle is A, opposite the largest side, and the smallest angle is B, opposite the smallest side. And since angles B and C are relatively close to each other, so are little b and little c. Let us do two problems from scratch. In number 13, we are given that angle B equals 160 degrees, little a equals 19 and little b is equal to 28. We realize right away that this is a side-side angle situation, and our first step is to draw the picture. The first thing that should hit you is that we are not given the traditional angle A and little b. We have angle B and little a and little b. It really doesn't matter. These are just labels. When we draw our picture, realize that angle B, being 160 degrees, is very obtuse, getting close to a straight line. So little a being 19 means that little b, 28, is about 1.5 times as long. So the picture that is drawn is not necessarily drawn to scale, but is somewhat accurate to the situation. We now need to use the law of sines to get angle A, as we have the complete B family and only half of the A family. So using that little a over sine of A is equal to little b over sine of B, we get angle A is equal to the inverse sine of little a sine B over B. And therefore, that is equal to the inverse sine of 19 sine of 160 degrees over 28. And we get 13.42 degrees. That makes angle C 180 minus 13.42 minus 160, and therefore it is a very small 6.58 degrees. Finally, we are going to use the B family and the C family to get little c. Little c is equal to B sine C over sine B, or 28 sine of 6.58 degrees over the sine of 160 degrees, and we get 9.38. So our final answer is that angle A is equal to 13.42 degrees, angle C is equal to 6.58 degrees, and little c is equal to 9.38. Looking at the picture, this appears to be right. Both A and C are very, very small angles, with C being very close to 0 degrees. And again, the largest side is 28, opposite the largest angle, 160, and the smallest side is 9.38, opposite the smallest angle, which is 6.58 degrees. In number 14, we're given that angle C equals 47 degrees, 13 minutes. Little a is 1 foot 10 inches, while little c is 2 feet 2 inches. There are a couple different things about this problem. First, again, the angle that we are given is no longer A, it is C. But that really doesn't matter, as we are given the entire C family and little a, making this a side-side angle problem. Secondly, our sides are given in terms of feet and inches. It is best to work with inches, so we will convert them to inches when we use our picture. So notice that in the picture, angle C is 47 degrees, 13 minutes, and little c, being 2 feet 2 inches, is 26 inches, and little a, being 1 foot 10 inches, is 22 inches. To solve, we will use the law of sines with the C family and A family. And angle A is equal to the inverse sine of little a sine C over little c, or the inverse sine of 22 sine of 47 degrees, 13 minutes over 26. When we get our answer, it will be in terms of decimal degrees. But since angle C was given in terms of degrees and minutes, we will convert to degrees and minutes using our conversion to degrees, minutes, seconds button, and we get 38 degrees 23 minutes. Angle B, therefore, is 180 degrees minus 47 degrees 13 minutes minus 38 degrees 23 minutes to get 94 degrees 24 minutes. Finally, little b is equal to c sine b over sine c, or 26 sine of 94 degrees 24 minutes over sine of 47 degrees 13 minutes, and we get 35.74 inches. Since A and C are given in terms of feet and inches, we will do the same with B, and we can write this as 2 feet, 11.32 inches. So our final answer is angle A is 38 degrees 23 minutes, angle B is 94 degrees 24 minutes, and little b is 2 feet, 11.32 inches. The largest angle is angle B, and that contains the largest side. The smallest angle is angle A, and the smallest side is also side A. And since angle A and angle C are relatively close, so are little a and little c. So that leaves us with case 6, the ambiguous case. That was a situation with SSA where we had 2 possible triangles. Let's review. We were given a side-side angle situation with angle A less than 90 degrees and little a is less than b. To find out whether this triangle is possible or not, we take a look at the value of sine b, which is little b sine a over little a. If that number is greater than 1, the triangle is impossible. It could be equal to 1, where it would be a right triangle, but as we said, that rarely happens. If sine b equals b sine of a over little a, and that is less than 1, there are 2 triangles possible. So that is the situation we are looking at. Looking at the picture, we see 2 triangles with the given information. Big triangle ABC and little triangle AB prime C. We need to solve both of them. As before, the first thing you would like to do is to draw the situation. Triangle ABC will be the acute triangle, and triangle AB prime C will be the obtuse triangle. We now solve the big triangle ABC in blue using the procedure we just went through. Let's repeat it. We first find angle B by using the fact that angle B is equal to the inverse sine of little b sine A over little a. Next, we find angle C by using the fact that angle C is equal to 180 degrees minus A minus B. And then we find big C by using the fact that C is equal to A sine C over sine A. We now will solve triangle AB prime C by using the following procedure. We start by finding angle B prime in triangle B prime C by realizing that that triangle B prime C is isosceles. So we find obtuse angle B prime in triangle AB prime C by using the fact that angle AB prime C is equal to 180 degrees minus angle B prime C. At that point, we can find little angle C by using the fact that C is equal to 180 degrees minus A minus B prime. Angle C will usually be a small value. Finally, we can find little c in the red triangle by using the fact that little c is equal to a sine c over sine a. It all sounds complicated, but usually you can do this in a couple minutes. Let's show two examples from scratch. In number 15, we are given angle A equals 38 degrees, little a equals 13, little b equals 21, a side-side angle situation. We draw the picture somewhat to scale, and it is fairly clear that little a, which is about 2/3 of the distance of little b, can be drawn to the horizontal in two ways, given the classic blue triangle ABC and the red triangle AB'C. We first go for triangle ABC in blue. Angle B is equal to the inverse sine of little b sine A over little a, which is the inverse sine of 21 sine of 38 degrees over 13, which to two decimal places is exactly 84 degrees. Angle C is 180 degrees minus 38 degrees minus 84 degrees, which is 58 degrees. And big C is little a sine C over sine A. 13 sine of 58 degrees over sine 38 degrees is 17.91. So our final answer is angle B equals 84 degrees, angle C equals 58 degrees, and little c equals 17.91. The largest angle is B, which has the largest side of 21. The smallest angle is A, which has the smallest side of 13. We now solve the small triangle in red, AB'C. B prime will equal 180 degrees minus 84 degrees, which is 96 degrees. And therefore, angle C is equal to 180 degrees minus 38 degrees minus 96 degrees, which is 46 degrees. Finally, little c will equal little a sine C over sine A. 13 sine 46 degrees over sine of 38 degrees, which is 15.19. So in the red triangle, we found that B prime equals 96 degrees, C equals 46 degrees, and little c is equal to 15.19. Since B prime is the largest angle, then it is opposite the largest side of 21. The smallest angle is A, which is 38 degrees, and that is opposite the smallest side, A of 13. If you draw your picture somewhat to scale, then a good check is to look at the picture to make sure that your answers make sense for both triangles. In 16, we are told that angle A equals 25 degrees, little a equals 11, and little b is equal to 14. We again draw our picture somewhat to scale, realizing that it is a side-side angle situation. The angle is smaller than was on 15, and the relative sizes of B and A are closer, which means that the small triangle is much more obtuse than it was in number 15. Again, we solve triangle ABC in blue first. Angle B is equal to the inverse sine of B sine A over A, which is the inverse sine of 14 sine of 25 degrees over 11. And we get 32.54 degrees. Since there was no mention of putting our answer in degrees minutes, we will just leave it in decimal degrees. Therefore, angle C is equal to 180 degrees minus 25 degrees minus 32.54 degrees, or 122.46 degrees. And finally, big C is little a sine C over sine A. 11 sine of 122.46 degrees over sine of 25 degrees, which is 21.96. So triangle ABC is obtuse, with angle B equals 32.54 degrees and angle C equals 122.46 degrees. Little c is equal to 21.96. Again, the largest angle, C, is opposite the largest side, and the smallest angle, A, is opposite the smallest side. So, in the red triangle, B prime equals 180 minus 32.54, which is 147.46 degrees. And therefore, angle C equals 180 minus 25 minus 147.46, or 7.54 degrees. Finally, little c equals A sine C over sine A, or 11 sine of 7.54 degrees over the sine of 25 degrees, which is 3.42. As we said before, this triangle is very obtuse. So we found that angle B equals 147.46 degrees, a large angle, so obviously angle C must be very small, 7.54 degrees. And little c equals 3.42, which is opposite the smallest angle, while the largest angle is B, and it is opposite the largest side.